Okay, let's get started. Welcome to the HAO Colloquium. This week we have very happy to have Dr. Margarida Cunha here. Margarida received her PhD in astronomy from the University of Cambridge, and actually her advisor was here a few weeks ago, and then went back to Spain, Portugal, to the Institute of Astrophysics, Space Sciences of the University of Porto, where you got your bachelor degree from. And as a researcher, and since 2012, she has been the PI of the research group on origin and evolution of stars and planets there. And her work has focused on the development of seismic diagnostic tools for inference of solar and stellar interiors, as well as on the interpretation of the coupling between solar stellar oscillation and magnetic fields. And I think it's on the latter topic you're going to talk today. Thank you.
Okay, thank you, and thanks a lot for giving me this opportunity to give this colloquium. I see this colloquium as a possibility to share with you the work that a number of us has been carrying out on the sun, that are actually visiting HAO now. And that's not only me, that's also Angela Santos, who's sitting there, and Pedro Avelino, who will be here until the end of December. And so if you have any interest in this work, do come and talk to us, because we'll be around. And actually, I should acknowledge that a lot of what I'm going to be presented has been produced by Angela. Angela is a PhD student in Porto that is working with us. So before I go on, I should warn you that the sun is by no means my field of expertise. So like you heard just now, I've been working mostly on stars, astroseismology. I started with strongly magnetic stars, and more recently I've moved into solar type and red giants. But I've always kept this interest in the sun from my PhD times, because when I was doing my PhD over 15 years ago, we did address just for a little bit the sun, and this same question that I'm going to be talking about now, which is, we were wondering what was the contribution of sunspots to the frequency shifts that are observed in the global modes of the sun along the solar cycle. Now, as it turns out, the answer to that question is not clear still today, and that's what brought us to this and starting to work on it. So let me start by revising some observations, and I'll start by the old observations and then move to the new ones. So what I'm showing here are results from the Nature 1990 paper that showed very clearly at the time, by comparing frequencies of the acoustic mode of the sun from 1988 with 1986, that the frequencies do change as the magnetic cycle of the sun changes, and that those changes depend both on the frequency of the modes steeply, and much less so on the degree, on the angular degree of the mode. And from these observations alone, the authors at the time were already able to conclude, draw two main conclusions. One of which is that whatever is causing these frequency shifts of the acoustic modes, it's originating close to the surface, near the photosphere, although not only on the photosphere, but also that the effect is strongest in the regions, in latitudes where active regions are seen. And of course, there's been a lot of works after that, based on much better data and on other methods as well. But in essentially, those studies have these conclusions remain broadly the same throughout these studies, with a lot more detail, of course. So moving on to what we know today, I show you here now the frequency shifts obtained from the Bayesian data. So this is ground-based low-degree modes data for 3 consecutive cycles, so just the 22, 23, and the part of the 24 that we have so far. The frequency shifts were published recently by Broomhall and sorry, I can't pronounce the second name. But anyway, but you can see they are shown by the black symbols, and you can see that they show the 11-year variation. And to compare to it, the authors plotted in red two solar cycle proxy, here the 10.7 centimeter flux, here the sunspot area, and they fitted those to the first cycle, to the cycle 22. That's why you see a better fit on that cycle. But in any case, you can see that throughout the whole activity, both these proxies follow quite well the frequency shift variations, or the other way around. The frequency shift variations are also a good proxy of the solar cycle activity. Now, you can, here you're looking essentially, or you're dominated by the large 11-year variation. But you can also see, and that has been pointed out by many authors, in the frequency shifts, a variation that is on shorter scale than that. And you can do that by yearly averaging this data and subtracting it. And then if you do that, you have, again, compared to the two proxies, again, the data on frequency shifts is in black, you can see a variation that seems to be on a period that is quasi-biennial. It has often been called quasi-biennial oscillation. I won't use that term because that term is used in different contexts with a different meaning that is not necessarily related to this one. So I will stay with the quasi-biennial helioseismic variations, okay? And, but basically the issue is that those quasi-biennial seismic variations are shown in these seismic data just as they are in the other proxy. Sorry, yeah.
I see those are low modes, so can you find these variations in stars?
I'm not sure. I mean, so far we've seen variations in stars, but it's not clear if it is on the main cycle or on shorter times, because I don't think we can say that yet. But yeah, in principle, you could, but I don't think we've got there yet. Maybe Travis will be able to say a little bit more about that, if you don't mind waiting for the end. Or do you want to say something else?
I'd say there's a clear detection in one star from color.
Is it? Yeah, for a cycle, but do we know if it is the whole cycle or if it is this quasi? We don't. That's what I was aiming to.
Because we haven't been doing it long enough.
Yes, I mean, yeah, Corot is quite short. And even in Kepler, for years, if you think of a solar cycle like that of the sun, you could eventually see these two-year variations, but you'd be in the limits, yes. So it really depends on, you'd have to go to shorter cycles, stars. Anyway, so the one question that I want to ask is what causes these variations, right? And people have discussed this a lot along in the literature. There's a number of papers about that. And essentially, you can expect to group them in two types of effects. In the direct effects, which would be the effect of the magnetic field of the Lorentz force directly on the pulsation motion, and the indirect effects, which would be the effects that the magnetic field has on the structure and dynamics of the sun, which in turn affect the oscillations, okay? And if you think of something like a sunspot, you will have both effects together. You'll have the direct effect because you have a strong magnetic field which will directly generate the Lorentz force that will affect the oscillations, but you also have the structural variations inside the sun, in the sunspot compared to the quiet sun, which will induce further variations. And so it is difficult when you have that picture of the frequencies changing along the solar cycle to say what comes from what. And the difficulty there, it's because everything goes together in this one parameter, which is the frequency shift, which you have along as the time passes. So what was our motivation to study the effect of the sunspots specifically on the global oscillations? So that means separating the effect of the sunspots from all the other effects that generate that frequency shift. Well, originally, the motivation was actually one that has nothing to do with solar activity. It was an indirect motivation. Basically, we wanted to use the low-degree L modes of the sun to learn about its deepest layers. And the low-degree modes of the sun, if the sun were perfectly spherically symmetric, and if you look at modes with the same frequency, the differences would arise only from the inner layers. The problem is that if you have at the surface a phenomenon that is non-spherically symmetric, highly non-spherically symmetric, as the sunspots, for instance, that phenomena will affect different mode degrees differently. And so now you compare modes of different degree, and not only you have differences that come from the center of the sun, but also from the surface. And we want to get rid of those. So the original motivation was to understand the impact of the sunspots on the frequencies so that we could remove it and use the clean frequencies to study the center of the sun. Now, that was 15 years ago. I kind of got Douglas interested in this again now when I talked to him a few weeks ago here, because he was the one that started me on this. But actually, our motivation right now is much more direct. We were hoping that by understanding and studying the effect of sunspots on the global oscillations, we could learn something about the sunspots themselves, so about the activity itself. Anyway, we'll see how far we can go with that. In any case, because I'm going to concentrate on the sunspots, the most important thing here is to understand how the strong magnetic field affects the oscillations, okay? Because that's what is going to make a difference between the sunspots and the other overall global variations. And there's been different studies of the impact of sunspots on the waves. People have studied it in different ways. For instance, in the case of the sun, Paul Cowley, Elena Komenko, Colados, and their collaborators, they have studied how a perturbation of fixed frequency coming through a sunspot, how it changes and how it exchanges energy between magnetic and acoustic waves and so on. I've been doing it in a slightly different way because I've been doing it for magnetic AP stars. And so the way I do it, but the result is the same. So the physical picture that I'll show you is the same. So what I've been doing is that I'm worried about the modes inside the star. And these are essentially modes, these are essentially normal modes, acoustic normal modes, so standing waves. And so the question I ask is how these standing waves are perturbed when they come to this layer where you have a strong magnetic field. And that means solving the equations for the pulsation equations with all the magnetic terms in the region where the magnetic field dominates. So what comes out of it, which is somehow similar in a picture to what people have found for specific case of sunspots, in a simple case I illustrated here, is that you have your acoustic wave, essentially acoustic wave in the interior of the star, of the sun in this case, and then as it comes up to near the surface, it reaches a layer where the magnetic pressure starts to get comparable with the gas pressure, or at least non-negligible. And at that point, this wave, if you actually look at how it changes, it's no longer an acoustic wave. It becomes a magnetic acoustic wave. And throughout the region where magnetic and acoustic and gas pressure are similar, that's what you're going to have. If you then go further up still to a region where the magnetic field dominates the dynamics, then this magneto-acoustic wave will decouple into different waves, some that are essentially acoustic, some that are essentially magnetic. The magnetic wave will be, in this case that I'm illustrating here, which is a case in which the perturbation is on the plane, is going to be essentially a compressible alpha wave, which is going to refract. Its energy is going to be kept inside the star because the alpha velocity is changing rapidly, and that gradient will make the wave refract back. The acoustic wave, on the other hand, will be able, depending on its frequency, to propagate out along the magnetic field lines and eventually dissipate. And the reason why it can, even if the frequency is below what we usually call the acoustic cutoff frequency, is because due to the way it interacts with the magnetic field and due to the fact that it has to go, the motion and propagation has to go along the magnetic field lines, here, the wave is actually seeing the atmosphere sideways. And when you see the atmosphere sideways, it looks much more homogeneous than when you look up directly. And so even for a frequency that would normally be reflected back because the stratification changes very rapidly, because you're looking sideways, it can actually propagate. And so you will have energy losses through these waves so far as the magnetic field is sufficiently inclined, and depending on the frequency of the wave. Okay, and then the coupling also results in magnetic waves, slow waves that dissipate when they get deep enough. So this is the general picture, okay? What the three main things that come out of this picture is that, one, if you're thinking about relatively low degree modes, and that can go up to L's of a few tens actually, when you get near the surface, if they were purely acoustic, the motion would be essentially vertical. Now, because of magnetic field, the pulsation velocity is no longer vertical. So you will have, in a strong magnetic field case, you'll have velocities that are not vertical, even if your original source was essentially vertical, and it would be in the absence of magnetic field. On the other hand, you have energy losses through this coupling process. But most importantly for the rest of the talk, if you think about this wave, which is the one that interests me, is the wave inside the star, or inside the sun, right, the acoustic wave. If you look at it, and if you ignore this layer and just ask how the wave looks up here at this boundary, the phase of this wave will be different in the magnetic and non-magnetic case as a result of this layer that is above it. And so if you are interested in how the frequency of the wave, of the global wave, changes, what you need to do is to compare the boundary condition, if you want, that you want to apply to the wave, so the phase of the wave here, when you have this magnetic layer above, with the case in which you don't have that magnetic layer. That will give you a perturbation that you can then use, of the boundary condition, that you can then use to say what how the frequencies of waves inside here have changed. Now, one important point here is that because the magnetic field direct effect is so important here, you cannot treat this as a small perturbation. So you cannot use perturbation theory to see the effect of a strong magnetic field. You can do it in the boundary below, but not there. So you'd actually have to solve the equations with the old magnetic terms in the boundary layer. And that has been done for the case of strong magnetic stars. So what is following on what I was saying here, so what you're going to have here is you're going to compare your magnetic with a non-magnetic case. You're going to say that there's this layer here for the moment. I don't care about it. I just care that that layer introduces a phase shift between the wave in the magnetic case and the wave at the non-magnetic case at this bottom, where the magnetic field is no longer important. And then I calculate this phase shift, and then I ask, knowing this phase shift, can I know what is the frequency shift that this phase shift induces on the waves? And you have to consider the whole region covered by strong magnetic field, which in the sun you will consider to be the spots, basically. And you can use the variational principle to do that relation, to make that relation. So you can show by applying the variational principle that the relative frequency change is just an average of this phase shift weighted by something that is related with the inertia of the mode, which I won't write it out here. But basically, the important thing is that you relate it with the average phase shift, where the average phase shift is the integral of the phase shift throughout the whole surface, weighted by the spherical harmonic corresponding to the mode that you are considering. Now, in a star that has a strong large-scale magnetic field, this means calculating the phase shift throughout the whole surface, integrating throughout the whole surface. In the case of a star like the sun, if I want to look at the sunspots effect, this phase shift will be zero throughout most of the sun, quiet sun, because I'm only considering a phase shift different from zero where there is strong magnetic field, but it will be different where every time there is a spot. And so this integral will be reduced to the sum of the integrals corresponding to each spot. So going for the case of the spot, if you want to calculate that phase shift, you have to assume some model for the spot, right? And here I'm showing you the magnetic field lines for a model from Comenco and Colados. This is a axisymmetric model, so I'm only showing the projection. So this is the distance from the axis of the spot, and this is the depth. Here is the photosphere. And you can see immediately that in this case, you'll have a phase shift that will be dependent on the distance from the axis, because the magnetic field properties, inclination and strength is going to be different. And you have two ways to go about it. One is to calculate from first principles this phase shift, meaning taking this model, considering both these both the stratification changes in comparison with the quiet sun and the magnetic field, and solve the equations in that layer and find this phase shift. And then you can integrate throughout the spot and find the average phase shift for this one. And then you can say, okay, but the spots are not all the same, so you can change the parameters on your model to see the kind, try to see different kind of spots or kind of phase shift induced, and then take a characteristic value to use, something like that. You're not going to do this for every single spot that appears on the surface of the sun, obviously. So you have to do some trick like that. We are working on that. I'm not going to show you any results of that just today, because we don't have the full results. We have done it already and published actually the indirect effect, so considering the spots, but considering only the stratification changes without the spots, without the direct effect of the magnetic field. And we found out, not surprisingly, that the indirect effects on the frequency shifts are relatively small. So now we need to look at the direct, putting everything together. So I don't have the results of everything together. So what I'm going to show you is another approach that we have in the meantime done, which is the lazy one, if you want, but very interesting as well, which is to say, okay, we don't want to calculate just yet this phase shift. So we are actually going to parameterize the phase shift. We're going to say that each sunspot basically produces a given phase shift, but then the effect depends on, it scales with its area, because we know this is an integral of the area of the phase over the area of sunspot, so we expect to be somehow proportional to the area. So we're just parameterizing this. And now we are going to use the observations to say if we can actually say something about this characteristic phase shift, which would be the characteristic phase shift induced by the typical sunspot per unit area. And then we could, once you finish this work from first principles, compare. So if you do that and you go back to that effect that I was telling you about, then your expression gets reduced to something like this. So you have the frequency shifts induced by spots for a given mode of a given L and M, basically is this characteristic phase shift weighted by the inertia, and then you have to sum all the areas of all the visible, all the sunspots that are at a given moment, weighted by the Legendre polynomial corresponding to the latitudinal position. So basically we have three elements here: the characteristic phase shift, the latitudinal position of the spots, and the area of the spots. Those are the three things. And what I want you to call your attention to is that this thing here and that thing there change on a very short time scale. So the time scale characteristics of sunspots, right? They can also change on the longer time scale, because the areas of the sunspots also change overall during the 11-year cycle, and the positions we know as well. They drift in a very specific way. So this function of time of these two things comprises two components: a short time variation and a longer time variation. This one here, we could also assume is a function of time, because we do expect that, I believe, along the solar cycle, the characteristics of the sunspots will change. That would induce a long time variation on this characteristic value. But we're going to not consider that at the moment, and we can discuss the implications of that. So we have our model for the now a parameterized model for the frequency shifts induced by the sunspot, and we want to compare with data. Now, what we want, of course, because the sunspots induced frequency shifts will be seen on a short time scale, we want to use the data that computes the frequency shifts on a shorter time scale as possible. And as it turns out, from what we could find, the Gong data is the one that offers that best. So we consider the cycle 23 from Gong data, published by Tripathi et al. 2011, in which they consider bins of 36 days. So each frequency shift they compute corresponds to an average of 36 days. That's long compared to the lifetime of the spots, but still we could expect that shorter time scales than those 36 will still show up when you do this average somehow, although reduced in amplitude, of course. And so we combine a number of frequencies, which we will consider in our model the middle between these frequencies, and a number of degree L's, which we will consider in our model. So the important thing to see here, to know here, is that what is this observable? So these frequency shifts, they have a precise meaning. What they do, as they usually do, is they take the multiplets for each mode, and they expand the multiplets in a polynomial way, and they take the central frequency, and they see how that central frequency changes with time. And that is the frequency shift here. And so in order to compare with this observable, we go through exactly the same process in our model. We compute the frequency shifts for each mode, L and M mode. We do the 36 days average, but we also do this expansion in terms that Tripathi et al. Do with the data, such as to isolate the central frequency shift and compare with this. So just that you know that we're comparing the same observable with what is observed. And we're going to consider two cases. In the first case, we're going to consider that everything that, all the frequency shifts observed in the sun are the result of the sunspots. Okay, so let's take that case first. And so we take our model, we calculate that observable. So we calculate frequency shifts for all the modes that they consider, we calculate that observable, and we have our observable as function of time, and we plot it and compare with the frequency shifts found by Tripathi. Now, the black are still the frequency shifts found by Tripathi. Let's focus on this panel now. The red is what we get. This is done by chi-square minimization. There's an obvious thing here that you notice immediately. This spread is huge compared to what the data shows. But that is perfectly understandable because we know from the beginning that the frequency shifts that are observed are not resulting only from sunspots. And so what we are doing here is that we're missing completely another component. And by adjusting that other component, we may be able to say what the component that is seen on these shorter timescales contributes to. So that's what we're going to do. So now, instead of considering just the frequency shift induced by the spots from our model, we add to it a global frequency shift. This global frequency shift is perfectly ad hoc. It's taken from a fit that Atway et al. Did to the data over the 11-year cycle, and so it's perfectly ad hoc. But so now we have two parameters. We have the parameter that enters our model, which is a phase shift, and we have the weight of this component, right? And so what we have now here is we do the fit of this model to the data by a chi-square minimization, and what we have here is the result. So in green is the global component, okay, and in blue is the spots component. So this is the proportion of the two components that makes the short-term variations in our model comparable with the short-term variations observed in the Tripathi et al. And if you see what they contribute, basically the short term, which we are saying comes from the sunspots, is about 30%. The long-term variation contributes by about 70%. Now, of course, there's a number of issues here. One of them is that you may say, well, but there are other things contributing to the short-term variation. For instance, there are other short-time phenomena, like the plage, for instance. The issue is that we believe, but we may be wrong, that the sunspots, because they are at the photosphere and they have strong magnetic fields that are inclined, they will have the strongest effect from the short-time variation phenomena that you can think of on the oscillations. Because in order to affect the oscillations, you need to have this effect preferentially in the cavity of the mode, which happens for the sunspots, and you have to have a strong magnetic field there, and inclined, which you have for the spots. This is not to say that other phenomena, short-time phenomena, does not contribute to it, and so in practice, this 30% will comprise the contribution for all the short-time phenomena, short-time being smaller than about the 36 days that we are averaging on here, okay? Yeah.
I was just wondering what are the physical parameters that are being optimized?
From the model, you have one physical parameter, which is the phase shift, which is the parameter that comes here. This is perfectly, is no physics into this. So this global component is taken from a fit, as far as I remember, to be honest. Maybe Angela can
Two free parameters here?
Two free parameters, yeah. And there's 36 day bins in 11-year cycle. Okay? Yeah.
Sorry, what range of modes is this?
So this is L's between 0 and 100, or yeah, I can go. It's 100, and frequency is also in a given range. Yeah.
And so, what depths, turning depths, do those correspond to?
Oh, they all turn below the sunspot. Well, assuming at the sunspot model that we have, which is a 10 megameter depth deep spot. So they are all. I mean. They will not all come vertically, probably, through the sunspot. So yes, you do have a mixture of modes, but we do go through the process of calculating the frequency shifts for all those L's and then compute the same observable that he has. Now, if you look at the residuals, if you compare the residuals in the two cases, you'll see that the residuals are quite large, even in this case as well. But they have a completely different appearance. Okay? Well, in this case, you have a scatter on short time scales. No wonder, because you're really not doing a good fit on short time scales. Here, the scatter is on longer scales. And we'll go to the detail of that in a minute. But I just want you to see that there is a clear scale here, which is much larger than the 36 days that we are considering as our short time average. Now, this variation here is actually, if you calculate, do an autocorrelation function, you'll see that you have a periodicity here of about 1.5 years, okay? And it's actually in phase with what other authors have shown to be the periodicity of the quasi-biannual variations in the oscillations. And so what we get from this plot is that our model is clearly missing a physical phenomenon that introduces variations on time scales of the quasi-biannual variations. That's not a problem, because all we wanted was to estimate the short-term contribution. And we see that the short-term contribution is about 30%, and this is relatively robust, independently of adding a component which varies on a significantly larger time scale. When I say robust, it can be 2080. So it's not robust to the one value, but is of the other. Yeah.
Sorry, that's again. 36 days. Sunspot lifetimes are months, right? Multiple months, 5 multiple rotations.
No, not necessarily. If they are short, if they are small, they will be days. Actually, only the very large will last several rotations.
The active region clusters live for months.
Yeah, but that's why I was saying that from the point of view of the effect we're considering, we are considering the sunspots and the short time. But it's true that if you have other active regions that are acting on a longer time scale, like the plage, for instance, that last longer, then they can contribute to this difference significantly. Yes.
Yeah, I mean, we see
Yeah.
correspondences between these quasi-biannual oscillations and active region clusters. So
Yeah. No. I'm pretty sure this comes from phenomena that we're not accounting for, and most likely from those kind of phenomena. Yes. But it's a longer time scale than the ones we are considering. So that doesn't change the 70-30.
sorry.
No, that's fine. But we want to go further than that. So if you go back to here, you'll see that, okay, the spread, the variation about the mean of the red curve of our model and the black curve is similar, right? But you can't quite see from here if, it actually goes down and up exactly pair to pair with what the data is doing, which is what we expect from our model. If these short variations are dominated by the sunspots, then we expect that the frequency shifts to increase when the sunspot area increases, and vice versa. And so you should expect to see in the data the same variation that you see in the model. And so we want to eliminate this component, the global component. But we don't want to do just an average and subtract like people do. We don't want to do averages. It's kind of ambiguous. It depends on the bins you want and so on. So we want to do something else. So basically, we consider 2 data sets. Remember that I said that it's 36-day bins that they calculate, but they are overlapped in 18 days. So they actually have 2 sets of independent data averaged on 36 days. So what I'm going to be showing on the left is always one set of data, and this is the other set of data. And because we are averaging on timescales that are larger than our sunspots, right? And so we are losing some information by doing those averages. Comparing the results on the 2 gives us a sense to how much we can trust the results, because we're doing averages of 36 days centered in slightly different times. So we're comparing averages centered on slightly different times. Anyway, so we have the 2 sets of data here. And what we want to do now in our model is to combine the frequencies such that we get rid of the global component. And the way we do that is by going back to our model and saying, if the short time scales variations are really the result of spot areas variations, then whenever the frequency increases, the area increases, or the opposite. And so whenever the area decreases, the frequency decreases. So I can take, let's go slowly through this because this is important for all the rest I'm going to say. So I can take 2 consecutive bins, calculate the difference in frequency shifts between those 2 bins, and then sum with the next difference. Except that I want to always sum positively. And so what I'm going to do is to multiply this difference by a weight that is either 1 or -1, depending on the spot area of the spots increasing or decreasing. In our model, if really the short time scales were generated by the sunspots alone, then we would always get the right sign, and we would always sum positively the bits, which going to these curves here means we would be summing all these little bits positively. You just take the length of this red curve and just take the length of the black curve. That's what we would be doing if there is a correlation. I will use the word correlation in the sense of the areas increase, the frequency shifts increase, the areas decrease, the frequency shift decrease. If the correlation were perfect, that's what we would have. So let me first do this to the model, just to convince you that that eliminates the global component. The reason why it eliminates the global component is because the areas increase and decrease, increase and decrease, increase and decrease, and the global component doesn't know about that. And so when you apply that, the global component is canceling out. But the short-term component is actually adding constructively, okay? And so we do this for our model. We compute this quantity that I was telling you about, the sum of the frequency differences weighted by S, considering both the frequencies of our model in which the global component is included, that's the blue, and considering only the contributions of the spots, that's the red, as function of time. And you see that the two lines are very, very similar. What this is telling you is that by combining the frequencies in this way, you are essentially canceling out the global component. You're canceling out because you're summing it and subtracting, summing and subtracting. It doesn't care about how the area changes, okay? Now, let's do this to the data and compare with the model. So again, our two sets of observations. Now, the red curve is the model. The black curves, the red curves, there two, are the model. The black curves are the data. Let's look at one of the panels. In the red curves for the model, the two lines, the dashed line is just summing the modulus of the variations. So it's just summing up, calculating the total length of that curve, okay? The continuous curves is applying, is this value here. So it's applying the S according to the area variations. In our model, the two lines are the same, because by construction, our models, the frequency shifts always increase when the areas increase and vice versa. In the data, however, the two come quite differently. That means that for sure in the data, even when you exclude the global component, you still have regions, that's when these two curves get more apart, in which the area of the spots is increasing and the frequency shifts is decreasing and vice versa, okay? Now, I point out here what you'd have in the average, the 1 sigma for a random walk, because in general you would have a value, even if they were completely uncorrelated, the variations in the area and in the frequency shift, you'd still have a random walk, right? And so you still could have a value different from 0 for these curves. But this is the 1 sigma that you get when you do simulations. And so this continuous curve, although quite different from the dash curve, it still shows a very strong correlation between the way the areas vary and the way the frequency shifts vary. So this is significant. But you cannot explain it totally with the variations in the area. And the same is true here. Now, there's a number of reasons why this could happen. One of the reasons is the one we've just discussed before. Short time variations may come from other phenomena that not the sunspots. If those phenomena are not exactly in pair with the sunspots, then by using the sunspots as a weight, we might sometimes using the wrong weight, right? So that could be one thing. But there is another obvious reason, which is we are taking the areas of the spots as seen in the visible disk only. But the frequencies care about the whole sun, right? So it could be that the area covered by spots in the whole sun is increasing, and then the frequency shift is increasing, but the area that we see is decreasing, right? And so you would lose correlation because you're using what you see and not the total variation of the area as a weight. And so we wanted to test if this was enough to justify the difference in these two curves. We cannot see the other side of the sun, And so we need to do simulations. And so we use the model, a parametric model that we actually developed for a completely different work to study stars, but which we calibrated on the sun, which generates a sunspot cycle and the butterfly diagram and everything. And we calibrated on the cycle 23 of the sun. And just, I'm not going to describe this model because I won't have time, but just to convince you that it's a reasonable model to use to test this thing that I was talking about, I show you here in red the results of our model for cycle 23 as compared to the results of the sun, what the sun is doing in black, and for the number of groups as a function of time, the area of groups, the latitude distribution, and the group area cumulative distribution. And so you see, we have a model to generate sunspot cycle, which we can use for this purpose, and to study other stars, which was the main purpose of it. Now, what we can do is we can take this model, calculate as function of time our sunspot cycle, so the areas at any given time, what is the area covered by sunspots, calculate the frequency shifts that using our model, that area would induce, but then calculate this other quantity, in which we're using the S as a weight, the variation of the area, by taking only the visible area. So by doing that, we're mimicking what we are doing for the sun when we use as S just the visible sunspot areas, okay? So by doing this, we calculate the simulation equivalent to the continuous curve. And then we can also calculate the sum of the frequency of the models of the frequency shifts, which is just summing the whole thing, and that will give us, for each simulation, the dash curve. And so we have the continuous curve, we have dash curve, we see how much they differ at the end, and we repeat the simulations many times. And what I'm going to show you next is the distribution of this difference, to see if that distribution justifies the difference that we observe. So if this phenomenon of not seeing the other side of the sun is in the origin of that difference that we see. So this is the distribution of that difference, and for the two samples. And the average lies in about 125 nanohertz. Now, if you compare to what we had before, you'll see that in either case, the difference between the continuous and dashed curve at the end is about 400 nanohertz. So it's well down here in this distribution. So that means that not accounting for the other side of the sun, when I look at how the areas change to calculate the S, can account for a part of it, a significant part, 150 or 100, whatever, but not for the 400. So there is some loss of correlation between how the areas vary on a short time scale and the frequency shifts vary, that is not accounted for by the fact that we are using the visible areas only and not the all areas, okay? Okay, so next question we ask, can we see when is that correlation lost? So remember that the correlation, in the sense that I'm talking about, that the two not going the same way, is lost every time this continuous curve gets away from the dashed curve. That's how you see it. If it goes down, if the black continuous curve goes down, you have an anti-correlation, a local anti-correlation. If it goes flat, it means you're essentially not correlated, and then you have to ask the question of how significant it is. But anyway, so one obvious thing to do is to subtract these two curves, okay? So I'm going to subtract the dashed and continuous black curves, which are our observations, summing always positively or summing using the area change as a weight. And I'm going then actually to differentiate it. But let's look first at the difference. So here is the difference between the two curves as a function of time. The arrows point the two peaks on the solar maxima. And let's look at this one, which I find more beautiful to start with. And have a look at another one. This is almost a step function. I mean, this you can see that in this case, if we didn't have this sample, okay, we would see that there is very precise moments in time in which basically the frequency shifts are not doing what we would expect according to the variations of the areas. When we look at this one here, it's not so clear. Remember that this one is just doing averages of the same size but centered on a different position in time. We do see that there is a huge variation near the maximum, and that is dominating that. But you can look further on this and actually differentiate these, because that will highlight how fast these two curves are getting away from each other. And if you do, you get this. So you can see that in this, which is just a reflection of the other one, so in this sample, you see that there are moments separated more or less the same way where you are clearly losing correlation. Here you also see the same moments, but you are heavily on the maximum. Yes, sorry.
Sorry to ask.
Yeah.
Can you remind me the difference between
The two. So they are two samples from Tripathi. So what Tripathi does is averages of 36 days, but it does these bins shifted by 18 days. So you have, okay, so it's 36 days average moved and phased by 18 days. And so it gives you an idea of, how much you can take out from this data because you're averaging on 36 days.
But they're very, the results of the two are very different, even though they overlap.
Yes, they are. They clearly, so that shows that the fact that you are doing 36 days average on phenomena that changes typically on days, the way you do the averages will give you different results. The way you put your filters will give you different results. Yes, Rainer.
So the magnetic interval, it's down there before it appears at the surface. So you're like, oh, sorry.
Yeah, no, I'm not getting there because I'm not going to show that here. The first thing we thought was that maybe the spots are affecting the frequency shift, the frequencies before they appear at the surface. And there is a phase shift, and we try different ways to check that, correlating with bins that are actually unphased with the bin of the frequency shifts. And we get some indication that there could be some phase shift, but we're not confident enough to show it or even to publish at this point. We'll still keep looking. We can discuss that. But yes, I mean, one possibility is that the same afterwards. I mean, you can have a different phase between the moment in which the spot is affecting the frequency shifts, the central moment, and the moment it appears.
Well, I think the frequency effect would be a wider function compared to the spot.
Oh, in the case, yeah, that too, yeah. Yeah, but we can discuss that, yeah. Anyway, so now what I'm going to show you is to guide your eye to the maxima of the quasi-biennial variations, okay? So these are the maxima. These ones, the white are the minima, the green are the maxima, okay? And if we forget about this, which we can't, okay, I would say that I don't know what you say. I would say that we have a signature here, again, of this thing that apparently is not canceled out with this trick that we do. We cancel out the global variation, but not this one, maybe because this one is correlated with the short time variations as well. This one also lies mostly on the red bins, although much more intensively on these two. But it still goes mostly on these ones. The exception is this one, which is also here, which hits the minimum of the quasi-biennial periodicity. Anyway, so we asked the question of whether this could, again, this lack of correlation, this loss of correlation could originate from these phenomena, in particular when the phenomenon is reaching its maxima. Remember that in white bins, the phenomenon is there as well, reaching its minima. I'm just throwing things into the table. This is ongoing work. We are working on it here as we are here visiting the HAO. So we'll be happy to talk a lot about that if you have any ideas. Okay, so that brings me to my conclusions and future work. So I think we are confident that the comparison between our sunspot model and parameterized model, I should say, and the observations tell us that the sunspot contributions will be about 30% of the frequency shifts that are seen, with, of course, the stating as well that other short-term contributions, if they are important, they would probably also appear in this 30%. We see significant correlation between the frequency shift variations and the area variations, but there are clearly moments in time apparently aligned with the quasi-biennial helioseismic variations where that correlation is lost. And for the future, of course, we want to calculate the phase shift from first principles, such as to compare with the one that we deduce from the observations. I didn't say what we deduce for the phase shift from the observations, because that phase shift alone doesn't mean anything. So for that phase shift, you need to take into account that it will depend on the depth to which you integrate, so that R star that I was talking about, where you position your boundary layer, and also on the frequency. So giving you a number, I can tell you that for the fit we did is minus 0.15 radians, but that won't say anything if you don't have all the rest. But we should calculate it and compare with the what we get from the observations. Because if from first principles, from the models, we get a phase shift that is comparable, we'll be happier to say that this 30% actually come from sunspots. If it turns out that it's quite different, then we'll have to reconsider and say it probably comes from sunspots plus other short-term events or mid-term events that also contaminate the short-time average. And also we'd like to consider a similar analysis dividing the frequencies in different frequency ranges, because these frequency ranges will be sensitive to different depths below the photosphere, and so it will be interesting to see, again, if we would find a different picture if you look, for instance, only for the lower frequency ones that are more sensitive to layers that are slightly below, like about 1,400 kilometers or something, where eventually other effects, like plage, wouldn't have so much effect, because these frequencies do not go, the modes are reflected further, slightly further down. And of course, we want to look at solar 24 cycle data to redo this analysis. And I think that's all I wanted to say.
How sensitive are your results to the specific assumption about the sunspot model? For example, one could ask if you took very different magnetic field configurations, either as a uniform field, horizontal, or especially inclined, as you were showing in the sketch, or if it's an additional sinusoidal modulation, for example,
from the point of view of what the result we're showing here, nothing would change, because I'm parameterizing the phase shift induced by the sunspot, okay? So I'm parameterizing it and obtaining it from the feed to the observations. But from the point of view of the derivation of the phase shift from first principles that we want to do and compare with these ones, it will depend significantly. It will depend on the inclination, because that magnetic coupling that I talked about depends significantly on the inclination of the field. If you have vertical fields and you have low degree modes, it will hardly affect, because vertical motion doesn't do anything to magnetic field. If it's too inclined, also the coupling is not so strong, because the decoupling will happen further up. And so the middle inclination, 30, 40 degrees, are the ones that work, that will impose a larger phase shift. And that has been found also in the works of Paul Cowley and collaborators. It's the same thing. And so, yes, if you change the structure of the magnetic field, you will change the phase shift. You won't change, assuming it comes from the sunspots, you won't change the dependence on time, though, unless you change the lifetime of the sunspots. Right? Then otherwise you won't change the dependence on time. But the range, the amplitude of variations, yes.
So where you get the divergence of correlation between frequency shift and sunspots? Have you looked at what happens at the surface of the sun?
We're just doing this, just finding some of the results.
No,
what we did look was at the flex, at the proxy. I didn't actually, unfortunately, I don't have the plots I could have shown you. So it is, if I show the one of the first plots, you'll see that the flex, the 10.7 centimeters flex, actually, and that several authors have pointed it out, seems to fit better the frequency shifts than the area. Now, this is sensitive to the chromosphere and to the plage and so on, as well as to the sunspots. And so we did do the same analysis, taking as weight not the change in the area of the sunspots, but the change in the flux. And you find that you lose less correlation. So indeed, we confirm that this is better correlated. And that is an indication that maybe plage are also are important for the variation, either the quasi-biannual or even the short scale. But you will,
maybe that it's a trace of what's happening below.
Or that, yeah. Or but you also find what was good. Oh, but you also say, if you do that other differences, you also find that you will lose more correlation, even using the flex in the same moments. You don't lose as much correlation, but it will be preferentially on the maximum of the quasi-biennial variations. But,
I will.
well, we'll talk. Yeah, we can talk.
The active regions emerging, where they get back into correlation.
Yeah, well, that's the kind. We'll discuss that, because that's the kind of that out of phasing. It's the kind of thing that we were working on. We can show you the results we have, but we weren't confident enough to write it in the paper, which is being written actually. Sorry.
I have a couple of questions. One is that I remember a paper in the late 1990s, maybe about 20 years ago, but by Douglas Goff, Marcus Rubin, and I think you.
That's when I started worrying about this. Yeah.
So I was wondering now, what the results you're presenting here seem a fair amount like that.
Yeah, well, let me tell you what the difference was, okay? So the difference, that paper has never been published. Only the preceding paper was published. So that's only a preceding paper. What we were looking at the time was to use the local seismology observations to constrain the characteristic phase shift. So we were doing a similar model, exactly. So the first part of my talk could be the same, but then when we get to the characteristic phase shift, which we're also taking it as characteristic, we're trying to get its value from local seismology. And what we were looking at the time we're looking at the results by Tom Duval, in which he considered at the time the correlation between a circle around a sunspot, rather than between the center of the sunspot, and which I think was what people started doing later on. So at the time he considered a circle around the sunspot, and he computed a phase shift. And so what I did at the time with Douglas and Marcus was to translate that phase shift from the US seismology to the phase shift from this work, because they are not the same. They are different things, but you can, using ray analysis, you can convert one into the other. And at the time, there were two reasons why we didn't publish it. Well, the main reason was that we all got busy doing other things, but there are other two reasons. One of them was that when you do this, you have to consider also that not all rays go through the sunspot. So you have the ray going through the sunspot, that's the most likely thing, but you have to consider all the other rays that might, with lower probability, that don't go to the middle. And so all we could get was a limit, a lower limit to the effect of the sunspot. And we were working on that calculation, how to compensate for that, and we never finished it. That was one of the things. But we could have looked at the minimum value. And I actually recently went to look back at it to see if it was more or less the same that I get from this. And it's not too far off. So that is a lower limit, and it's not too far off. But the other thing that worried us at the time was that it was not clear from Tom Duval's paper if what he was calculating was the phase shift or the group, so just the phase wave shift or the group phase shift. And what we wanted when we transform it into this phase shift is the phase shift, not the group shift, okay? And it wasn't clear from his papers that that's what he was giving. Because he had to model the envelope and the wiggles, and it's the wiggles that we insisted on and not the envelope. And then we also needed that for a range of frequencies that was very small, because we were looking at eigenmodes. And so recently, I was talking with Takashi and so on to see what are people doing in local seismology these days, because I'm not working on the sun. Can we redo this? And also with Lohan, Gizon, and so on. But the feeling I had is that the way they do it now is different from what I need. So they look at packets of waves going through the wave, so going through the sunspot. So it's not a specific frequency that we could associate with a particular eigenmode. And also, I think they are looking at the group velocity and not a phase velocity mostly. But I'm not completely into it, so I'm not sure. Maybe there are things there, and we can redo that work and check. That's another way to go about it. Yeah.
Okay. Well, that's a good answer.
Sorry, long one. But
that paper was no less interesting. It was certainly published enough to be very interesting.
it's a, yeah.
But the comment I wanted to also make was that other experiments, like Doug Brown, looking at local correlations between waves that are thought to have from the quiet sun, bounce off of the sunspot, and then come up somewhere else. In other words, those kinds of experiments indicate that the signature from flashes is considerably greater than that of the sunspot, maybe several times, because mainly because the flash takes up a larger area.
Yeah, of course. So there's the area effect. My question to you is that true for the frequencies that I'm looking at? Because for higher frequencies that propagate, the issue about the sunspots, my argument for the sunspots being potentially more important, but that's something I would like to look at, because as I said, as the sun, I'm not expert on the sun, and so these things are somewhat, I need to get fed on those, on that information. But the feeling I have is that if I have a relatively low frequency mode, right, it will essentially bounce at the photosphere or even below, if it is like below the before. So exactly, and so it will fill the sunspot, but it will only fill the plage on the tail. Okay, of course the two things are connected. So if it fills the sunspot, part of the energy will leak up, and then it might be influenced. The whole thing might be influenced from the plage. So I'm not ruling that out. But I would expect that result to certainly be true if you are at high frequencies, where the modes, even above the cutoff, but below, but high, near the cutoff frequency. So my question is, do you find that also for, say, a 2 millihertz type of interval, or around?
That's a good point.
It does vary with frequency. I would say for this frequency range, 2.5 to 3.5, for modes that are a little bit higher than this, if you want to go to intermediate range of around 40, we have maps, daily maps from the far side of the sun, which show you the phase shift over that entire hemisphere.
Okay.
So that's another data set that I think would be very, very relevant.
Yeah. Okay.
For this kind of stuff.
So we should talk about that.
That's a good point. But now, those actually maps don't distinguish between sunspots and flaws.
Right, yeah, exactly. But it's everything.
And so we see this variation on the near side. It's quite strong for both sunspots and flashes. But I don't think we've taken a good look at how that variation differs between the sunspots and flashes.
Okay.
So, for example,
So that would
go to low frequencies, it's possible that the flash disappears before the sunspot.
Yeah.
Or whatever.
It would be very interesting, because also the fact that this correlates better with the flags are an indication that the plage are important. Whether they are important as the shortest time scales or at the biannual case, then it's a different story. And maybe because plage last longer, they will be more important for the intermediate. But if we can fix that, I mean, anything, it will be interesting to discuss. Yeah.
But it nevertheless, I think it's worth emphasizing that at least for a certain range of frequencies that we look at a lot, and somewhat higher L's than what you're talking
about. That's also a point, because the higher L's they are much more superficial.
But nevertheless, that the plage seems to be, because of the greater area, the cumulative phase shift from integrated over area is several times, 2 or 3 times probably. That's a guess. What it is for sunspots in a typical active region.
Yeah.
And so I think that is going to happen.
Okay. Now, it would be nice to discuss that. Also, we have to see how that phase converts into the phase that I'm talking about here, because it's not the same thing. And so we need to see, and that brings me back to the other work that we've done many years ago, which we tried to convert one into the other.
Naive question. Looking at phases, does that mean you're doing essentially adiabatic observation?
Yeah, yes. So the phase shift that I'm considering, using the variational principle, I'm assuming they are adiabatic oscillations. Of course, that doesn't mean they don't lose energy, because they lose energy from the boundary conditions, right, above. But whatever happens above is translated into a phase shift, and then that is applied to the adiabatic calculations inside. But I think it's safe to use the adiabatic calculations inside.
My question would then be, what about the energy equation? How much the amplitude of these energy cycles with these oscillations, and do those tell you anything about the coupling with the upper atmosphere? If energy is leaking out sideways through
No. The energy that is leaking out is taken into account in the phase shift. The phase shift is complex here, and you have a decrease in the amplitude. If you do from first principles, like I did for AP stars, for instance, then no, the phase shifts are complex. But what is taken into account there is the energy losses through the traveling waves rather than the local non-adiabasities. Okay, and so that's the only component that is taken into account. But that affects the phase shift, of course, that energy losses.
I mean, would you have an issue or expect to see surface effects related to this from the point of view of the energy equation? I mean, I know people are talking about bouncing off a different boundary condition and flight and stuff like that. Mm-hmm. That's a slightly different issue, but that's what you mentioned. I'm just wondering to what extent, I mean, the total irradiance of the sun changes by 0.1%, 0.08% or something over the cycle. You know, the chromosphere in Corona takes up 10 to the minus 5 of solar Ionosphere. And we still see all these 5-minute oscillations of that transition. We shouldn't really do that because they're very tightly constrained over the top of the supergranular cells. So it's really not a horizontal field.
Yeah.
So, the coupling between the interior and the external atmosphere, I think, is something that's pretty damn interesting.
No, it is.
Confusing, right?
Yeah, the problem is the complexity that it brings to the problem, but I completely agree with you.
Examination energy equation should be able to eliminate that.
Yeah, I haven't looked into that problem. But
personally, the corona has nothing to do with the internal structure of the sun.
The whole issue of the effect of the fact that hydrodynamics becomes non-adiabatic. That is a really annoying issue that certainly needs to be attended to. And because the thermal conditions in sunspots and collages are significantly different. You can't just say, well, let's subtract it from everything.
No, I mean, from the point of view of this analysis, because I'm just parameterizing, I'm saying that whatever is up there that influences the phase, including non-adiabasities and stratification, is comprised in that. So I'm just a parameter that is function of time. But if to do from first principles, yes. I mean, for instance, in the magnetic model that we're using from Elena Komenko, I have no consideration is made whatsoever about the dynamics. So basically, all we have is a stratification change, pressure density, and the magnetic field, which is there and makes a direct effect. But anything that has to do with changes in turbulent pressure and so on, forget it. It's not there. Apart from the reflection in the gradients of the stratification. So yes, to do it from first principles, accounting for all those problems, it's a complex issue. So.
A brief comment about the differences between the two data sets that we saw. Correlation with the quasi-biennial variation. I wouldn't be too concerned about those differences because
no, I'm not. I think
okay.
They're expected. I think they're expected. That's what I mean.
The reason I wouldn't be too concerned is because it's not just the timing of the maxima of the quasi-biennial oscillation matter. It's also the amplitude, and the amplitude varies basically with the 11-year cycle.
Yeah, I know.
So the fact that you see in both data sets near the maximum, where the amplitude is large for the quasi-biennial oscillation, the fact that that's important.
Well, but that's the point. It's not so much in the second one. In the second one, the amplitudes are pretty much similar in all beams. It's only on the left one that you see that. But the reason, you see, the amplitudes here. So this is the maximum of the amplitude of the quasi-biennial oscillation, okay? And these are all pretty much the same. The reason why I'm not worried is precisely because of that change of amplitude and other things. If you move your beam, the center of your beam a little bit, the way you are averaging the short time scale effect will be different. And so in some cases, you might pick up, in fact, a larger amplitude in here, which is what happens in this case. And in the other case, you might not. And so
I think that in the case on the right, you basically just got lucky.
Yeah, that's what we thought. That's why I said, this is the right phase to.
If you did a full range of all the possible ways that you could fit the data, you would always find those two.
Yeah. No, I agree. Here, this is a lucky case. We actually classify it that way.
In our simulation some time ago, we looked at the numerical Eigen functions, and we had two that corresponded to the one from John's model came to 1626. And at the lower end, there was a little difference in the photosphere. Whereas for the higher end, there was hardly any.
The higher end, you mean?
For the larger end.
Oh, N, larger N, okay.
Simulation and the model ones were essentially identical to the photosphere. For the smaller end, there was a little difference.
Okay. The smaller end would be the one that wouldn't feel so much these layers, actually, right? So those are the ones you say that.
So this was including both the effects of the radiation.
Yeah, everything. Okay.
Thank Margarida again.
Thank you.